All right. So, yeah, just to mention, this work was done in collaboration with the Technical University of Chemnitz and my supervising professor, which is Mr. Professor Otto. Okay, so basically, my agenda for today consists of 4 points. I'm just introducing my novel actuation concepts for micromirrors, and then I will talk shortly about the design I developed in the last years, and then here are some slides about characterization of the manufactured MEMS device and a short summary and outlook. So, for 2D MEMS scanning micromirrors, there are a lot of promising applications, like, for example, virtual interactive displays, augmented reality, 3D scanning, and LiDAR applications. For all these, there are mostly quite harsh requirements concerning power consumption, maximum voltage for consumer electronics, the overall dimensions, and cost especially. So what happens if you want to project an image, like in the image on the left, is you have to perform a 2D line scan, which just, it's like in the old days in the cathode ray tubes, basically, where you have one fast scanning axis projecting the lines, and then you have a slow quasi-static axis that shifts between the lines in a slow fashion. And that's the challenge, especially in MEMS. You always have a problem if you want to deflect your device in a static manner. And that's what costs power and what leads to too large size of the device, because, yeah. Oh. So that's how the problem is solved in state-of-the-art Bosch technology. You have two mirrors attached to each other and aligned to each other. Both are driven electromagnetically. So there's one mirror which is quite small that is able to deflect statically, and one larger mirror that deflects resonantly. Yeah, this is one way to do it. What could be the other way is having both functions integrated into one device. So that will save a lot of space and cost. But so the way to do it will probably be electromagnetic. So you will have coils integrated. Let me show you again. Coils integrated into this blue frame, which is then deflecting statically, and use the Lorentz force for actuation. And that costs energy, and you need a permanent magnet. So what we proposed is why not using indirect static actuation, which is based on the gyroscopic effects, as shown on the right. So yeah, for those of you yeah, I mean, it's not quite, well, sorry, not quite clear what's going on here. Let me explain you in detail. So we use a resonant axis right here, which just performs the line scan, as I've told you before, with large amplitude. And then we introduce a second resonant axis, which is parallel to the mirror normal, and with similar frequency of about, like, well, maybe 50, let's say 50 hertz more than the primary resonant axis. And what happens then is that the angular momentum of the primary axis is disturbed. And if you get the phase relation right, then this will lead to a quasi-static deflection about a third axis perpendicular to the form 2. by just exploiting the conservation of angular momentum. Okay, so much to the concept, which is one thing. If you want to design this into a MEMS chip, there are several challenges to overcome. So first thing is you have to choose a proper MEMS process. In our case, it looks like that. So there's probably a diffusion diffusion and metallization process, which is just a semiconductor front-end process. Then we introduce a piezoelectric material for actuation. In this case, lead zirconite titanate. And then we have a first trench process. So as you see here, there's a buried oxide. So we use a silicon non-insulator material, and we have the buried oxide as a stop layer. Okay, then we bond a cap for mechanical protection and handling, and then we turn the wafer around and do a grind polish step. So grind down the backside of the wafer, and then we do a second trench to, we're kind of modeling a second mechanical layer out of the backside of the SOI material. And then a last wet edge release. And as you see here, we can have like 2 degrees of freedom just from the 2 mechanical layers more. Okay. Once again, so we have piezoelectric detection, we have an SOI process, we have piezoelectric actuation, and we have 2 mechanical layers for additional degrees of freedom. Coming to the actuation. So what I use for the primary resonant axis is a piezoelectric actuation. It looks like that. So it's basically a mechanically coupled oscillator with these actuation beams here with mass elements placed on the ends and the mirror element in the center. And then you get like 2 different eigenvalues for that system, leading to a parallel and an anti-parallel mode. I will use this parallel mode for actuation of the out-of-plane axis. And then, well, that's quite easy, comparably, but to drive the mirror and deflect it in its plane, it's another story. So I developed a actuation scheme that looks like this. So we have electromagnetic actuation in this case, and we have 4 coil elements with a radial segments. And if you have a current flowing through these, then there will be some kind of Lorentz force in the presence of a magnetic field, as depicted here. So that gives you a torque. It's just a preliminary actuation concept for proof of concept. Okay, so to the design. As you can see here, that's the piezoelectric actuator again. It's like the core in the middle, and I twisted the actuator beams around the mirror to minimize the dimension. And then there is a static axis built around this core element that will be deflected by the gyroscopic torque. Okay, and for the in-plane, we have coil elements here, and on the other side again. All the blue colored parts are like the backside, the second mechanical layer. That is just the purposes for stiffening mostly. Okay. All right. And as I told you on the second slide, the beat frequency now defines the quasi-static deflection frequency. Okay. Now we place some piezo-resistive Wheatstone bridges here for detection, and that allows some closed-loop operation later for characterization. Okay, coming to characterization. After manufacturing, the chip looks like this. So, well, basically, you can really see the difference between the. Oh, that says 4. Okay. 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 So yeah, that's my setup. I have a laser here, an FPGA board running a closed loop algorithm, which is basically PLL, and then the image is just projected. The beam is projected onto an optical screen. The results look pretty promising. So we get an out-of-plane deflection of about 40 degrees point of view, and an in-plane deflection. It can't be measured optically, so at least not directly. So I just got the feedback from the piezoresistive detection. There's some trick. So if you have 3D vibrometry available, then you can measure this effect optically as well. And that led me to a deflection of 0.2 degrees, and then you can you can compute the bridge sensitivity out of that. But as you can see, there's some damping in the curve, which is basically package damping. So that can be improved by a factor of, I hope, by a factor of 2 or more in the future. And that's the image. So what you see here is basically that's the out-of-plane axis driven by piezoelectric actuation, and then you can. So the horizontal is basically the indirect static actuation driven by the gyroscopic torque here. Okay, to summarize, we've designed a novel micromirror device driven by indirect quasi-static actuation. We've got samples manufactured and characterized with promising results, and an actuation and deflection of about 2 degrees in the moment, with plenty of room to higher deflections. And for outlook, this concept still uses electromagnetic actuation, which adds a permanent magnet to the package dimensions. That's going to be replaced by PCT in the future. Yeah, I'm going to increase the fill factor, and we're running some experiments on decreasing the damping to achieve higher static deflections. Thank you.